I will introduce the presentation of Professor Muralee Murugesu. Hi, Muralee.
Hi, good morning. Can you hear me?
Yes, I can see you. Let me introduce to the audience about your background, please. Professor Muralee Murugesu received his PhD from University of Karlsruhe, Germany in 2002, under the guidance of Professor Powell. He undertook several postdoc stays, firstly at the University of Florida, and then at the University of California in Berkeley, under the supervision of Professor Long and the Nobel Prize Professor Prusiner in 2006. Then he joined at the University of Ottawa, firstly as assistant professor, then associate professor, and finally as full professor. Muralee has an age index of 51, and he has reporting more than 200 high impact papers related to nanotechnology, lanthanide MOF, single molecule magnets, and diverse materials with optoelectronic application. So I will introduce in Spanish also. El profesor Muralee actualmente trabaja en la Universidad de Ottawa. Actualmente trabaja en diversos proyectos relacionados con MOF y complejos con aplicaciones en optomagnética. Su background es muy extenso. Terminó su doctorado en la Universidad de Karlsruhe en el año 2002. Realizó estadías postdoctorales en la Universidad de Florida y en la Universidad de California. Y actualmente trabaja como profesor con un cargo full en la Universidad de Ottawa. So this is a pleasure to listen to you in this ArMOF conference for first time. So you are welcome, and you can proceed as you want.
Okay, thank you so much. Thank you, Herman, for the kind introduction. And I want to start this talk thanking the organizers and inviting me to this first meeting. Hopefully we can do this next time in person. I really would like to. I do love to coming to South America, and if I can come back to Argentina for sure, I'm not going to miss that opportunity. But in the same time, you guys are also welcome to Canada. We're pretty much well vaccinated country, so hopefully we'll be out of this mess soon, and everybody is welcome as well in Ottawa. And if you want to do collaborations in different fields of material science, you're welcome. So I just put the background of Ottawa to entice, a little bit of a tourism to show the Parliament Hill. So we are still under the reign, in quotes, of Her Majesty the Queen of England. So you can see the Parliament Hill and the Ottawa River and the beautiful sceneries. And currently it's very beautiful outside because of these trees are turning red, and the scenery is quite spectacular. Anyway, just to show you today some of the work done in my group, and I want to focus your attention on this little video, which is a slowdown video of 100 times slowdown of an energetic materials, which is a droplet of energetic material into an accelerant. And this accelerant basically initiates our energetic materials to create or release the large amount of energy packed into this material. So this is one of the research areas that we develop in my research group, but also one of the largest research direction we conduct in my group is basically single molecule magnets. These are magnetic molecules, and they act like a nanomagnets. So this is something quite cool. We are interested in developing these nanomagnets for molecular electronic application. This is something that we envision to, for example, implement into memory storage devices such as hard disk or even quantum computing. The other area of research, which is compared to these two research areas, is slightly smaller in metal organic framework that we also like to investigate for their confinement properties that we can explore. One of these, by the way, if anybody is interested in doing energetic materials research, with these Defense Canada, as well as these large defense corporations such as the General Dynamics. I'm always looking for organic chemist. If you know a very good organic chemist in postdoctoral level or even PhD level, we are more than welcomed. This is a research developed with my colleague Jacqueline Brousseau as well. So anyway, the common theme between all these materials is to develop new materials with tailor-made properties by design. So that means we can create materials that can be designs that will, but also modified in order to optimize their functions. So MOFs, I'm not going to give you an introduction in this meeting. These yellow balls inside metal, coordination polymers became famous as MOFs. And one of the things that we are specifically interested in, what happens inside. Can we visualize what goes in, and also can we understand the host-guest interaction between the MOF and the guest molecules within the framework? So that is something that porosity surface functionality is something that we are always looking for. And we know all the hundreds of different potential application in this field. And one of the particular application we are interested in, MOF in crystallography. This is crystal-free crystallography that Fujita made it famous in 2013 in this article, where he was able to, or his team was able to capture some small molecules and get some X-ray diffraction data of the guest molecules. So this is something I will present towards the end of this talk. So this is all started for me when one of my friend Mircea Dinka and my previous lab worker or lab mate in Berkeley, when he started his research in MIT, he reported this system while we were also investigating this MOF5 for magnetic property reason. But Mircea was investigating how this MOF5 can be modified. For example, can we replace some of these metal ions such as zinc into titanium, chromium, or iron, any of these first row transient metals that he was able to show by soaking for several weeks, if not months, to absorb and site replace some of these zinc atoms. So we thought, what would be nice. By the way, these structures have been resolved by powder XRD and computational methodology. There was no single crystal report at that time. So we were wondering, is it really possible to see what happens to the zinc site when there is a different atoms comes nearby? Does it stay stable, as often claimed MOF5 being stable, but we weren't so sure of this feature. So what my student Rebecca Holmberg did is basically doing this reaction of MOF5 with a small percentage of iron nitrate in this reaction. So it's almost like a dilution type methodology, where we were able to get these beautiful cubic orange crystals, which is reminiscent of the MOF5, and the structure is clearly shows an interpenetrated MOF5 system. So we know that MOF5 can crystallize also in an interpenetrated framework, but now you can see this interpenetrated framework is linked by these orange balls and these two which represent the iron, and the two oxygen atoms which is linking these interpenetrated frameworks. I'm not sure. Can you see my cursor, Herman? When I move the cursor, can you see it?
Yes.
Okay,
I
great.
can see it.
Okay,
Yes.
okay, thanks.
No problem.
If you look carefully at the unit or the tetrahedral unit of the MOF5, that the new one we call it here IMOF5. So basically you have the same zinc 4 unit, but one of the zinc, instead of adopting a tetrahedral environment, now it's adapting almost square base, trigonal bipyramidal geometry, where one of the oxygen atom is linking the ion center. So of course, we have tried to do several data set of the X-ray diffraction and including even synchrotron diffraction. What we found out is this electron density is quite clear. We can also see these ones, but around the ion center, it was difficult to probe. And we needed to know what is the oxidation state of the ion. by looking at the color, you can say it's orange, so it should be iron 3 plus as an inorganic chemist. And then we can also do EPR as well as most power spectroscopy to elucidate this. From the isomer shift and the quadrupole splitting, you can clearly see that it is an iron 3 plus ion, and also the G value obtained through the EPR clearly tells you when it's 2.0, it's an isotropic metal ion, which means this clearly in iron 3. If it was an iron 2, we will have an anisotropic G value, which will indicate spin orbital coupling present in this iron 2 systems. Here we have a clearly 9-3. So what's the environment around the ion? This is something that we seek help with my colleague Tom Wood to find out what is these atoms around these ion centers. So through computational methodology, they were able to find out these three oxygen atoms belongs to a hydroxide group, which is kind of surprising still to me because terminal hydroxide are not so common. We would have expected these to be water molecule and these to be hydroxide. But the lowest in energy they were able to obtain through this modeling is this structure. So we do believe through one thing for sure, it is iron 3 plus ion, which is present, and it's also linking the tetrahedral unit of these two interpenetrated framework to form this stable MOF5. So just to mention that I went quickly that the thermal stability of MOF5 is around 470 degrees Celsius. Now, due to these linking of this interpenetrated system, you're going much higher in thermal stability for this system. So what about if we create a new system using an asymmetrical linker? Can we create new magnetic MOFs? Why do we really need magnetic MOFs? Something that I've always wondered, because if we can create porous magnetic MOFs, then you will be able to create porous magnets. Porous magnets mean lightweight magnets. Lightweight magnets are highly desirable in terms of application. So we sought to use cobalt, which is highly anisotropic metal ions. In this reaction condition, we were able to get these triangular unit where you can see the cobalt center is equivalent crystallographically. Therefore, you have antiferromagnetic coupling also in this system, which lead to a delocalized system in this case. But unfortunately, this MOF wasn't very stable, so it decomposes very quickly. Slightly changing the reaction condition, adding 1 drop of HCl to this reaction condition and heating it at a higher temperature, we can make this beautiful supercube SBU for this MOF. And if you look at the structures, these SBUs are linked by this asymmetrical linker into 3-dimensional to form this UBT framework topology. So when we got excited about this structure and thought like this is one of the coolest SBU that I have personally seen, and it is formed with magnetic metal centers of cobalt. So we hope that we will have a nice metal organic framework that act as a magnet. And unfortunately, when you look at the spin density of these systems, these 4 of these cobalt ions are antiferromagnetic coupled. That means the spin centers cancel each other. As you can see in the susceptibility times temperature versus temperature, which is the chi-T versus T plot, you can see the chi-T plot decreases with decreasing temperature to lead to a singlet ground state. So it's overall, it's a bit of a dull magnet, or if not even a magnet, it's an antiferromagnetically coupled system. Again, it's the biggest disappointment that we had at the time, and we started to get discouraged about this field of carrying out in these porous magnetic MOFs. So by then, we realized that we are missing an interesting point of this asymmetrical linker, which is basically if you take a carboxylate and you see these metal oxygen binding distances, it is very similar to the triazole metal oxygen binding distances. And also the bite angle is very similar. But one key difference is the charge. When a carboxylate brings -1, whereas a triazole base linker brings a 0 charge. So what if we take a framework that is made with dicarboxylate or any carboxylate and replaces with our asymmetrical linker? Therefore, we will be able to change the whole charge of the framework. So instead of creating a neutral system, we can take a neutral system and make charge framework. You might wonder, why do we want charge framework? Then you can trap highly toxic anions. For example, if you make a cationic framework. So here is this framework that initially you saw with the cobalt, if I may go back, this framework, and I mentioned this is unstable. But if you can take a TPT ligand and basically stabilize this framework, here the TPT ligand acts as partitioners, but also holds together and form this framework with a pack net using this benzene dicarboxylic acid. But if you change it to CPT, this is asymmetrical linker, now you are retaining the packnet, but now the charge is changing. It's become a cationic framework, which means we should be able to do anion exchange systematically, put some anions and exchange with it. And this is the ideal scenario for us. We wanted to do asymmetric ligand exchange of a known framework while keeping the framework and the pack same, but only playing on the charge. Can we do that to this methodology? And we wanted to prove that proof of concept, we can exchange these anions. But we also can modify the spaces between these framework. That means you can change the porosity and the size of these pores by simply changing different asymmetric linkers. You can go from this to this one, and there's much longer system. And every time you can get beautiful single crystals that are highly diffracting, and you can do these anion exchange systematically. So here's the infrared data. You can see UART1, what we call it, which is basically made with this system. UART2 is made with this ligand system, and UART3 made with a third ligand system. And you can see different anions leading to the different characteristic IR stretches you can see here. And also, we were even able to probe the location of the anions using the single crystal data. You can see here the bromides are location of this, and the perchlorates and isothiocyanates are shown here. One key feature that we have to remember is the anion binding affinity. You can see the nitrates are the weakly binding anions, whereas thiocyanates are in this series is the strongly binding anions. So this is going to play a critical role. If you have a strongly binding anions, then you should be able to stabilize a framework that is not previously not stable. So as a proof of concept, what we did is we took our UR3, for example, containing a BF4 as an anion, and put it into the pipette as a small homemade filter, and passed through some of these tetrabutyl ammonium thiocyanate to see how much BF4 is exchanged with thiocyanate. If we looked at the series here, thiocyanate is a stronger binding anion, therefore it should replace most of it, ideally all of it. And you can see this is before running the column. Here is the solid state NMR of this ArMOF here, showing that BF4 is present. Then after, in the solution at the bottom, of course, we don't have any fluorine NMR detected initially. But the moment we started flushing through with a solution containing chloroform solution containing tetrabutyl ammonium thiocyanate, and this is the thiocyanate is now exchanging here with the BF4 minus, and then you can probe the BF4 minus here, and no BF4 anions are detected in this leftover afterwards. So it's pretty much almost 100% exchange with this anion exchange. So this seems to be working well, but what about the porosity and the stability of this system? So this was done in collaboration with Professor Shimizu in Calgary, because we didn't have at that time our own setup to do this. What we can see here, when it comes to the nitrate frameworks, we see here the BET surface area shown here is much lower than the predicted one or calculated one. And all of these cases, this is a bit disappointing. That bit tells us it's not very stable. But one thing is clear, when you have these nitrates or the bromide anions, you have this reversibility or hysteresis. Basically, the hysteresis tells us the mobility within the framework is leading this hysteresis, or maybe the partial collapse of the framework. And whereas if you have a strongly binding anions, such as NCS, then the framework is stabilized. And this is, you can see in this table of the BET surface area, more you go to the stronger binding anions, you are stabilizing the system. Now this BET surface area is much better. So in this case, above 40 kilojoule per mole of binding energy, you are stabilizing your system. So although this is somewhat that showing that it is exchanging, the stability is still a concern for us. So one thing we are currently trying to do is with our new setup, this is a little bit of a promotion for my laboratory. Basically, we have a new setup of micromeritics that we can do a gas absorption, physics option, as well as chemis option. Here is an classical activating methodology that we use for this instrument. But if your MOF is highly unstable, we can also use the supercritical CO2 dryer, that where you can use the solvent exchange using the CO2 dryer, which is a milder condition, which stabilizes or keep it stable, the whole MOF, in order to do these experiments. So that's, we can do that. So in case you are interested in collaborating, send me an email. I'm happy to look into it and then help you guys out. So final part of the talk, I would like to concentrate on a technique, what we call it crystalline sponge method. This I mentioned earlier on. This is developed by Fujita. So what we do is you take a MOF crystal and you soak it in a liquid that containing your guest. And after soaking, you take your MOF crystal and put it back on the diffractometer in order to probe the guest inside the framework. So you can do single crystal X-ray, and this is the TPT ligand again used in this MOF made famous by Fujita. There are two different frameworks. Fujita mentions the cobalt and the zinc, they work well, both of them, in this crystalline sponge method. And we wanted to test out if this is works for us as well, and if we can do something with it. And when we investigated the cobalt MOF, first of all, there are several structural transformations we discovered. Unfortunately, this is not as stable as it's claimed. So the cobalt one is basically, if you do this reaction as reported with dichlorobenzene in methanol, you can get these crystalline sponge of the reported MOF, but which quickly transform into the semi-amorphous material, which is dark green, when you remove from the mother liquor. And if you do a slow evaporation of the methanol, then you are changing into orange crystals. Basically, it's a two-dimensional framework where the sheets are slightly moved from each other and forms this a two-dimensional framework stack on top of each other. You can isolate the single crystals also using chlorobenzene instead of the dichlorobenzene, and isolate the nice single crystal of it. This is the methodology for crystallizing, and this is nothing new. This is a report. So the framework itself has the different units of these SBUs. You can see M6L4 unit or M12L8, or even much larger unit that can act as a cavity for gas molecules. But if you want to do crystalline sponge method, we need a system that is stable. You should be able to take the crystal out and put it back into a different solution to be able to soak it in. But as you can see in these pictures, that within 10 minutes or even within 5 minutes, you see the color change of this cobalt MOF. And this color change leads to a decomposition. And by the time you reach these above 6 minutes, it's completely amorphous in this system. So this was a bit disappointing for us, but we still wanted to understand the two-dimensional framework are shown here. The critical thing happening is while the methanol evaporates, some of these coordination sites are replaced in this framework. This is why, which leads to a transformation of the 3D framework to the 2D network here. Here is the side-by-side comparison of the 3D framework as well as the 2D network. And of course, it is a cobalt system. As we like to investigate the magnetic properties, you can see the coordination environment of each cobalt center is octahedral. Here, all of them are surrounded by the nitrogen atoms of this framework, the original framework. And this is a modified framework here, where two of these TPT ligands have been replaced by these oxygen atoms in this case. One interesting feature is if you probe the dynamic susceptibility measurement, which is if you want to probe if your system acts as a magnet, you do dynamic studies, which is AC susceptibility studies, where you make the alternating current as a medium to probe the relaxation dynamics. In a way that if your system has a magnet-like behavior, there will be a blocking of the temperature, which we call the blocking temperature. And below that blocking temperature, the material will retain its magnetic memory, i.e., you will have the relaxation mechanism in the AC data as shown here. This is the out of phase susceptibility in function of frequency, and this is the in phase. And these frequency dependent signals clearly indicate that you have a magnet-like behavior for this MOF, where the magnet-like behavior is arising from a single unit of this cobalt ion, which are barely connected in terms of magnetically speaking. These are not communicating, but the magnetism is arising from each individual cobalt center. So this is a potential use in the future if we can create magnetic MOFs. Perhaps magnetic separation is also an avenue that we can explore. So what we learned from this cobalt system, we just found out it is really difficult to work. It is unstable. But what about the zinc system, the analogous zinc compound that Fujita reported, which is an interpenetrated framework which has a reversible swatching behavior. That means if it is interpenetrated, you can think about the stability. Of course, it is much more stable, but also you can have these intricate framework where the pores are ideally partitioned to accommodate gas. And if you look at the channels here, in these channels, you see these nitrobenzene molecule, which is a solvent of crystallization. They pack in a beautiful arrangement to form this electron density here, you can see, which can be removed to accommodate new gas. So can we do that? What we were able to do is to confine ferrocene and ferrocene aldehyde within this framework by simply taking the zinc framework and soaking into a solution containing ferrocene. Although Fujita reported that you have to activate the MOF first, I can tell you for this case you don't need to. The solvents of nitrobenzene comes off without even activation by the moment you start soaking. So it is much more milder approach than activating the MOF first. When you look at the X-ray structure carefully, how the ferrocene or ferrocene aldehyde is located, you can see these in host gas interaction as shown here, and some of them are high occupancy site and some of them are low occupancy site, and you can see clearly the interaction between the framework and the gas molecules. Some of these pi stacking is happening here. So what we wanted to know, once the molecule is inside, is it stabilizing? Is it the structure is more retained in terms of the CP? Is it rotating? So what we wanted to find out through solid state NMR, through dipolar defacing technique, we were able to probe the crystalline ferrocene and the guest that is a ferrocene within the framework, that the dipolar defacing time changes drastically. You can see here the decrease here, while this is much longer in terms of dipolar defacing times, which leads to the conclusion that within the framework, the ferrocene molecules rotates much faster than when they are in a crystalline state. This can be rationalized simply because when you have a pure crystalline ferrocene, you have the stacking within the crystal structure of the pure ferrocene is much more dense. It is tighter stacking than within the framework where the molecules are able to rotate. So what about gaseous molecules? Can we put some of these gaseous molecules and see? What we sought to look not just absorption of gases, but more dynamic absorption. Can we probe stepwise how the gases is penetrating this framework, and can we look into this? So when you expose to the iodine vapors, you can see this is the original MOF, pale yellow. Quickly, within few minutes, you can see the color change, and within 1 hour, it goes to dark black crystal. And you can see the edges is still very sharp. So we had a bit of hope that it retains its crystallinity, and we should be able to see once the crystals are exposed to 1 hour of iodine vapors and then do the single crystal X-ray diffraction. And that's what we were able to do after 0 hour of exposure, that this is the original MOF, and 3 hours exposure, 6 hours exposure, and 15 hours exposure. Just to tell you, this is 6 months of work of X-ray data. Each one of them we collected at least 5 times in different diffractometers to make sure what we are seeing is not an artifact. And we can clearly see that after 3 hours, the MOF itself has these iodine anchors in the one of the zinc atoms. And you can see another one. This provides a really nice anchor for these I2 molecule to come and clip on and form I4 type motif. You can see here. And one interesting feature is you're going from a much larger volume to a smaller volume in this case, and of course the space group changes. That's because these iodines are bringing these pores within them and then collapsing in a way, not without collapsing the whole framework, but just bringing these closer, so the unit cell is becoming smaller. This is after 6 hours. Again, you can see the volume changes. Now the number of nitrobenzene is leaving slowly, you can see, whereas the concentration of the iodine molecule found within the pores are increasing over time. And this is 15 hours exposure. And you can see the iodine, now we can even see I3 type motif also forming. And now after 15 hours, no nitrobenzene is located. And we try to collect after 20 hours, and we lost crystallinity completely at that point. And unfortunately, we couldn't go back either. And furthermore, we wanted to do calculation to make sure that what we are seeing is correct. But through computational methodology, we were able to find the binding energies. So strong halogen-halogen interaction is seen here. And in this case, is 26 kcal per mole of I2 molecules are shown for these type of motifs. And you can see the X-ray data. This is the calculated data in brackets in terms of bond distances. And one interesting feature is, even though this is much higher in energy, the MOF is swelling. That means it's modifying its structure to accommodate even more iodine within the framework. So it is dynamic. It is not like, some of these MOFs, they capture CO2 and get captured in that position, and they are locked in. Whereas this guy here, it's rearranging itself to almost take up more iodine. It's almost like a system. He wants to keep chewing on these iodine and capture more and more iodine within the pores. And by doing a simple gravimetric method, we can see clearly that this ArMOF is one of the highest absorbing iodine system out there. And we can see how dynamically it's absorbing in terms of the I2 molecules are replacing some of these nitrobenzene, and you can crystallographically visualize. And physisorb and chemisorb iodine are seen within the framework, and it can take a really large amount of iodine. What this teaches us is basically, if we want to do iodine capture, it is ideal to create a system that has an iodine as an anchor within the framework, and this iodine clips on it and enables further. So I believe my time is coming up. With this note, I would like to thank my group. First of all, they do an amazing job, and most of this job is done by this gentleman here. Is Gabriel Brunes, recently graduated. And all these group workers, they all participate in some way or another towards each individual projects. They are amazing group of guys. I'm very grateful for their help. And also key collaborators, George Shimizu for initial gas absorption studies, as well as Professor Wu for computational studies, and all these funding agencies. And you can see this is a Canadian maple turned into completely red. And now this is what it looked like, most of the trees here. So you're welcome to Ottawa whenever you would like. Thank you, Elma.
Okay, thank you, Professor Muralee, for your amazing talk. It is also good to know the facilities in order to make some collaborations between the group in Argentina and your group also. This is good to know it. This is amazing, the fact that your system acts as a real sponge, right? I have a question about that. How is the stability of the systems upon remove the anions, the different anions?
Oh, this system with the anion.
Does it collapse?
So you can see that you can replace one anion with the other. That exchange is possible, but the framework is a cationic framework. So it inherently needs some anions to keep it stable. So you can do an ion exchange, but not completely removal, because what we are trying to do is we are trying to create a different linkers that are redox active. That means we can do without putting and doing an anion exchange, but we are trying to create frameworks based on radicals so that you can do a redox active with a more stable system. This one you have to always have an anion inside. If you have a redox active framework, you don't need to have an anion inside initially, and then you can put the anion in and you can remove the anion in, and that's a system that we are working on currently.
Okay, nice. And I can see that you have good cavities in order to functionalize with maybe aromatic compounds in order to improve maybe optomagnetic properties. This is correct?
Absolutely. You're bang on right. I only showed the setup that we have in terms of gas absorption, but with some of my colleagues, we were able to acquire a lot of instruments for magnetic property studies. We will soon have 3 magnetometers, 3 squids, as well as low temperature luminescence studies. We can do all the way up to 1.8 Kelvin luminescence studies under magnetic field as well, using an MCD techniques that we have now. So we are well equipped to do all kind of physical property characterization on these MOFs and other systems.
Okay, nice. I will check some questions from the chat or maybe YouTube. Let me see. Okay, I have a question from Celeste. She's an organizer from ArMOF also. She said, thank you very much, Professor Muralee, for your very interesting talk. I was wondering if you could tell us some additional details about the experiments performed to determine the binding energies of the different exchange anions in the MOF. I mean, how is the protocol to determine these values?
So let me. So here, what we have is the surface area analysis. This is the calculated surface area. This is the experimental BET surface area, which basically tells us when you have nitrate, which is the weakest binding anion, you have a very small surface area. When you go to bromine system or bromide system here, you are going much slightly higher in terms of surface area, and so on. So this is validated systematically through these different frameworks. And these binding energies, these are calculated binding energies using computational methodology. So based on that, and based on our chemical knowledge that we already have, plus the surface area calculations here, we can clearly draw an anion binding affinity here. And this is why we made this proof of concept. If you have a BF4, which is in this scale that I showed you, which is a lower binding affinity than NCS, we should be able to replace by NCS. And same way, if you have a nitrate, we should be able to replace by any of these here. The key idea is to remove toxic anions, such as chromates or things like that. And of course, we need to do much broader series of studies. First of all, experimental studies from BET surface analysis, computational studies, to be able to, and also some of these studies that we have done using NMR to show that how much is getting trapped and how much is exchanged here quantitatively. We should do that too.
Okay, thank you so much. Let me check. Okay, I have my only one question for me. In this case, I know that you are working with high energy materials. Okay, what is your opinion about the future of MOF in this area?
That is a very good question. So there are MOFs that people report them as energetic MOFs. That means they can ignite or explode or something like that. But one key factor, MOFs are inherently porous, right? And which means they are lighter and the density is lower. What you want in an energetic material is high density, because you don't want to pack, let's say, a rocket booster where you have whether it's a rocket for missile intercepting systems or things like that. You want the fuel to be dense, small, rather than a massive canister for fuel, which would take up most of the space. So density is a key factor, which doesn't go hand in hand with MOFs. But now you can tell me, but what if you create a MOF and put inside the MOF some energetic fuels, such as hydrazine? Then I would say, now we are talking. Then you should be able to increase the density of the system. And then this is the future, in my opinion, in these energetic materials based on MOFs.
Okay, thank you. And I can see that the TCP ligand is special for this application, for the nitrogen around.
Yeah, but unfortunately, TCP still has a lot of carbons. So what
Yes,
we're
of course.
working is extremely high level of nitrogen-based system. Unfortunately, I can't talk about these. These are contract with defense companies. And these are highly nitrogen rich with ideal oxygen balance, because you do need oxygen as well to optimize the performance. But we want to minimize the carbon, because if we have carbon, then we are producing CO2. So we want to have green energetic materials. So we minimize the carbon content in this. The TPT or CPT system, they are not ideal in terms for that reason.
Okay, Professor Muralee, thank you so much for your amazing talk. This is a pleasure to listen to you again, and we hope to see
Thank you.
you in the future in
Thank you
other
so much.
projects.
Thank you very
Thank
much.
you.
And thanks again for the invitation and for your attention.
You're welcome. Then, Matthias,
Hi,
are you here?
everyone. Thanks a lot, Muralee, again. And we're now moving on the last part of the today's session. And remember that after lunch break, we will have perspective talk with Patricia Orcajada. So stay tuned after lunch and come back, please. Now we will have 3 speakers in our flash sessions, and the first one, in order to introduce her, I will do it in Spanish also, because she's from Argentina, although